In this lesson, we're going to use a design brief to solve a problem that your calculus teacher has presented you. A major concept in calculus is creating a volume by revolving a known cross-sectional area around a specific axis or by adding cross-sections of known geometric shapes. These problems are illustrated in textbooks, which can only be presented on a two-dimensional surface. It is often difficult for students to actually understand the volume created, even with illustrations. Your calculus teacher has the ability to purchase three-dimensional models, but they are often expensive or do not coincide with a specific problem in their text. For this problem to be solved, we will use your Autodesk Inventor program and its parametric model capabilities, along with a 3D printer and a calculus textbook to create specific models for your calculus teacher. The problems taken out of a calculus textbook must be identified and the equations used to define the boundary region to be revolved. A .stl file will be created and used to print off the solid. The first type of model we'll create is a volume created by revolving a known area around a specific axis. This problem uses the curve y equals e to the negative x, the vertical lines x equals 0 and x equals 1, and the horizontal line y equals 0. That will be revolved around the x-axis. In order to use the Inventor program's equation curves feature, we need to understand the syntax of putting in equations, functions, and constants that Inventor will recognize. This page illustrates the algebraic operators that Inventor will accept, along with examples of how units are handled. Inventor will also follow specific orders of operations in complex equations. Correct syntax is important to define your specific problem. Autodesk Inventor supports many types of units. In calculus, it is very important to understand the difference between degrees and radians. Here, you can see that Inventor will accept unit prefixes. Also, the common functions you'll see in calculus class are defined, along with a proper syntax. Also, reserved system parameters such as pi and e are explicitly written in a specific way. We're now going to start Inventor to create our first 3D model. Once Inventor is open, we're going to create a new parts file. Next, we're going to start a new 2D sketch. Because we're used to working with the XY plane, we're going to select that as our working plane. Notice our menu appears, but there is no option for creating an equation curve. This is found under the Line menu. Select Equation Curve. You now have a menu that has different inputs you can provide Inventor. In Inventor, you have the options of using either parametric or explicit equations. The advantage of parametric equations is that sometimes curves can't be explicitly written for y in terms of x. Also, parametric equations will let you define x in terms of another variable, which can be useful in modeling some solids. In this lesson, we'll explore creating models by using both parametric and explicit equations. Let's begin by using the explicit, which you may be more familiar with. We want to create a solid that is bounded by the curve y equals e to the negative x, the vertical lines x equals 0 and x equals 1, and the horizontal line y equals 0, to form a region which will be revolved around the x-axis. We're going to first import our y equals e to the negative x curve. From our functions, prefixes, and algebraic operators cheat sheet, we see that Euler's constant lowercase e must be entered as a capital E. But also notice the warning triangle that popped up. Clicking on this shows that Inventor is looking for units. The easiest way to define a unit for x is to divide by 1 with a specific unit attached. Notice our sketch appears and our warning symbol has disappeared. Once the curve is drawn, it is important to set the domain of x, so you only draw the curve as long as the problem defines. In this case, x min is 0, x max is 1, which is what we are looking for. Repositioning shows our curve exactly how we want, so we're going to accept that. Now remember, we need to define a region to revolve, so I must graph the other boundary equations. For this, we'll use the line tool. The first we'll sketch is the x equals 0 line. Then we'll sketch the y equals 0 line. And we'll finish up with the x equals 1 line that intersects with our e to the negative x graph. We will now finish our sketch. We now want to revolve this region around a specific axis. To do this, we will choose the Revolve tool, and the profile is already selected that we want to revolve. We must now select the axis, which will be the y equals 0 line, and we will do a full revolve to create our three-dimensional model. Except, we can reorient, and then we can also observe from an angle that will show our three curves, e to the negative x equals 0, x equals 1 boundary line, and the hidden boundary line is the y equals 0 that goes to the center of our revolution. We can now save our model as a .stl file for future printing. To do this, we'll go up to our Save As menu. We're going to save a copy as. And underneath our Autodesk Inventor drop-down menu parts, we can find the .stl file. We'll name our part. And we'll choose Save. After the .stl file is printed, you now have a three-dimensional model of your calculus teacher's problem. Here, you see y equals e to the negative x curve, the x equals 0 boundary line, the x equals 1 boundary line, and there's the hidden y equals 0 line that we revolved around. For the next problem, we'll use a similar process to create a model, but we'll use parametric mode instead. In this problem, we'll create a region bounded by the curve y equals x and y equals x squared. This time we'll revolve around a different axis, in this case the y equals 3 line. Returning to Inventor, we'll create a brand new part file. We must start a new 2D sketch and select the XY work plane that we're used to using. Next, we need to select equation curve. Notice Inventor defaults to parametric equations. Notice you are no longer defining y in terms of x, but x in terms of t and y in terms of t. If we make x take on the values of t, then when we define y in terms of t, we really are defining y in terms of x because x is the same as t. Let's define x as t and y as t. This will graph the y equals x curve. Also, we must put our boundary in knowing that x0 and x1 is the domain that we want for this problem. Accept, and you see our line. Now let's create a second equation curve. This time we're going to define x as t and y as t squared. Notice for our t min or our x min being 0 and our t max and x max being 1, both curves meet at their endpoints. If they had not, I would have had then to change the values of t so that the two curves did meet. Also notice that I did not have to define units as I did in explicit mode. The UL that you would see sometimes under the Tmax stands for unitless. If I want to see what the default unit is, or if I want to change my units, I can select Show Units box. In this case, I see that I'm in inches, which is what I want. I have now defined a region to revolve. So accept. But I do not have, or I have not constructed an axis to revolve around. In order to do this, I need to create a line at y equals 3. To do this, I will choose my line curve, and I will draw a horizontal line at y equals 3. I will now finish my sketch. I will choose to revolve. I must select my profile to revolve, and then I must choose the axis to revolve about. I want to do a full revolution, which I will accept. And reorientating my figure, you can see that I have a curved outer surface of y equals x squared, and I have a linear inner surface of y equals x. We can now save our model as a .stl file for future printing. Again, save as, save copy as, look for the drop-down menu, .stl, and we will name this one y equals 3 axis. Save. As you can see, after printed, we have our three-dimensional model, which shows the outer curved surface and our linear inner surface. The final problem we'll be creating is a volume of a region of known cross-section. Here, we will generate a solid by creating a region in the xy plane between two curves. One, y equals x squared, and the other is y equals 8 minus x squared. Notice these curves intersect at -2, and on the other side of this, it will be x equals 2. As we increase values of x from -2, we want to build squares perpendicular to the xy plane so that the height of the squares is the same as the distance between the two curves. This can be seen in figure 8.22. Therefore, our model will not only be curved in the xy axis, but also the xz plane as well. To do this, we need to open a new Inventor file. We'll create a new parts file, and then we'll create a new 2D sketch. This time we'll begin in the XY plane again. We're going to create parametric equations. So we'll go get our equation curve, and we're going to define x as t and y as t squared. This time, as you can see, our curve doesn't go for the whole domain we would like. Therefore, we need to set our Tmin to be -2 and our Tmax to be 2. This way, we can be ensured to have the whole boundary region that we are looking for. So, after changing those values, we can accept this drawing. We'll create a new equation curve. This time, x will be, again, our t, And y is going to be our second equation, which is going to be 8 minus t squared. We once again have to change our Tmin from 0 to -2, and going all the way up to our Tmax of 2. As you can see, we now have created a boundary region. So we can accept this sketch in our drawing. It is important to notice that the maximum width of the square will be 8. Therefore, the maximum height of the square will also be 8. Finish the sketch. We next want to extrude the enclosed area to a distance that is equal to the maximum height of the squares to set the distance in the z-plane. Select Extrude. And in this case, it gave us 8, which is what we want. If it was something different, we would have to change the value to 8. By changing the orientation, we can see the base plane, which is the XY plane, and the two parabolic curves. We can also change to see the XZ plane and the height of the squares. Notice the height is constant, and we really want it to change as the distance between the two curves in the XY plane also change. To do this, we must create a new equation curve, but on a plane perpendicular to the XY axis that passes through the points the two curves in the XY plane meet. That can be seen right here. I'll readjust the view so you can see the plane we must create. We'll go through these 2 points and all the way back and along. First, we need to select the plane tool. If we move our cursor over the intersection of the XY plane curves, you will see a yellow point indicator appearing. Select each point in the XY plane with a left mouse click and one point in the XZ plane. This creates a new work plane. We are then going to select and start a new 2D sketch on that work plane. Notice I want to define my curve in the positive x and positive y quadrant. Create an equation curve by defining x as t and y is the distance between the original two curves. That equation is 8 minus t squared minus t squared, which really turns out being 8 minus 2 times t squared. There is an issue because the XZ plane shifted the geometry with between 0 and 4 instead of -2 and 2. So to compensate for this, we'll just shift the 8 minus 2t squared graph to the left by using the equation 8t minus 2t squared. All that does is it provides a shift between the -2 to 2 domain, which originally we wanted, to 0 to 4. We must now increase our domain values, and you will see that the entire curve, if we accept it, is defined that goes from x equals 0 to x equals 4, and the height of this curve is going to be the same as the distance between the two curves in the XY plane. We will now finish our sketch. Finally, we will use the cut tool and extrude to shave off the volume we do not want to leave the three-dimensional model desired. We'll reorient so we can see the work plane that we want to extrude on. Go to Extrude, select the surface we want to extrude. We will make sure we cut all the way through and in both directions. Accept. And notice that leaves our new three-dimensional model that is curved in all the planes we want. First of all, the parabolic X and Y plane, and also we want to look at it in the XZ plane as well. We can now go to File, Save As. We're going to save a copy as. We will call this cross-sectional area. Cross-sectional area volume. Choose a .stl file. Save. And now we can go to a printer and print off. As you can see, both models show the XZ plane curve, and this is the XY plane, two curves in the parabola. So now you have the skills to use Inventor to create 3D models. Now on to the Calculus Models Design Brief. You need to now complete all the parts of this design brief, beginning with designer, problem statement, and design statement, and list all the constraints that you'll come up against to solve this problem. You're then to go through the same process using your own problem that you have identified, and when complete, you can then move on to conclusion questions describing what part of the design process was most difficult, all the way through to describing other uses for this method besides making your calculus teacher models. Good luck.